All right, good morning, everybody. So by now we've already copied down the warm-up onto our packet. Let's go ahead and turn to page 2 in your packets. And what we're going to do is we're going to look at some equations. We're going to look at the symbols, and we're going to complete the data table that you see in front of you in order to help you with the electromagnetic fields and forces calculations that you will do on pages 7 and 8. So let's go ahead and look at our data table. I've got my first symbol here, which is F. And by now, I hope that we know that F is the symbol for force. And we know that forces are measured in newtons. And the symbol, or the abbreviation, for newtons is simply an N. Our next symbol, which is a new one to us, is a capital B. And capital B is a symbol that represents the magnetic field. Okay, now the magnetic field is measured in the unit Tesla. And the abbreviation for Tesla is a capital T. Another unit symbol that we're familiar with is a capital I. We saw capital I when we were talking about circuits. Capital I still represents current. And current is measured in amps. And amps is abbreviated with a capital A. Our next symbol here is a capital L. We haven't actually calculated with anything with an L, but we have measured other things with length in meters. So capital L in this case just simply stands for length. So we'll be talking about the length of a wire in some of our problems moving forward. So that is length measured in meters, just like distance or displacement. And the symbol is a lowercase m. My next symbol is a lowercase q, and we've seen that one before. That one represents charge. So this could be the charge that's running through a wire. This could be the charge of an electron or the charge of a proton. Q is measured in coulombs, which is abbreviated with a capital C. Lowercase v is one that we've seen before. Lowercase v is velocity. Velocity is measured in meters per second. And abbreviated lowercase m/s. The next one here is a capital V, which we have seen before. Capital V is voltage, measured in volts, symbolized with a V. And our last one here is N. N is, again, not one that we have seen yet. N represents the number of coils in a transformer. And the unit is just expressed in turns of wire or coils of wire around a transformer. And there's really no abbreviation for turns, so we'll go ahead and leave that one blank. Okay, so looking up at the top here, I've got three equations. I've got F equals QVB. So according to our data table, I've got force equals charge times velocity times magnetic field. So anytime that I am discussing or trying to figure out how fast charges move or how fast current moves, anything related to how fast it moves or anything that has a charge, you will use this equation. Okay, this is the only equation that's got charge or velocity in it. our next equation is force equals BIL. In other words, the electromagnetic force is equal to the magnetic field times the current times the length. So a lot of times if we're talking about a wire, we'll be given a length of wire, and the current that's running through the wire exerts a magnetic field. So the magnetic field times current times the length of that wire can give me the magnetic force. And here you have some helpful info. The charge Q for an electron and a proton is 1.6 times 10 to the negative 19. That same value is true from our electrostatics unit. Okay. If I look quickly, let's see here. So back to the left side. Let's look at our first example. So my first example says that humans emit a magnetic field because ions move through the blood. Suppose an electron was east by a standing person at a speed of 3.9 times 10 to the 6 meters per second. The electron is affected by a magnetic force of 1.9 times 10 to the negative 22 newtons directed to the north. How much of a magnetic field does this person emit? Okay, so it's a long question. It's got a lot of information. Let's just take out the information that's given to me. So the first thing that I see is it says an electron whizzes east by a standing person at a speed of 3.9 times 10 to the 6 meters per second. So this is telling me the velocity of that electron. So lowercase v is 3.9 times 10 to the 6 meters per second. Okay. It also goes on to tell me that the electron is affected by a magnetic force of 1.9 times 10 to the negative 22. So that information is telling me the force, which is F, 1.9 times 10 to the negative 22, measured in newtons. It says how much of a magnetic field does this person emit? So it says how much of a magnetic field. So in other words, I'm trying to solve for magnetic field, which is a capital B. Magnetic field is B. So at this point, I've got F, I've got V, and I need to solve for B. Well, when I look back up at my equation, at the top, the only equation that's got V is this one. Okay, I don't know anything about the length of the wire. I don't know anything about current, so I'm not using this equation. This is the only equation I can use based off of what I have, but something is missing. I've got V, I've got F, I want to solve for B, but what about Q? Well, if I look at my equation, or my word problem here, it's telling me, or it's talking about an electron. Okay, and we know that electrons have a certain charge of 1.6 times 10 to the negative 19. So that right there is my Q. 1.6 times 10 to the negative 19 coulombs. So now I've got the pieces to my puzzle. So my equation is F equals Q times V times B, where I substitute F is 1.9 times 10 to the negative 22 equals Q, we said was 1.6 times 10 to the negative 19. Velocity is 3.9 times 10 to the 6. And I'm solving for B. Okay, so if I want to get B by itself, but it's being multiplied by all of this, then all of this has to come to the other side. So what I'm going to do is I'm going to take this and divide it by itself. So this is 1.6 E negative 19 times 3.9 E6. So what happens here is that everything here cancels out. And I end up with 1.9 times 10 to the negative 22nd divided by 1.6 E negative 19 times 3.9 times 10 to the negative 6. I'm sorry, not negative 6, positive 6 equals B. So when I do the math, I calculate 1.9 E negative 22 divided by the product of 1.6 E negative 19 and 3.9 E 6. I get an answer of 3.04 E negative 10. And since I'm measuring magnetic field, this is in Tesla. 3.04 E negative 10 Tesla. Okay, now moving on to the next problem here. I've got a wire that is 1.5 meters long, carrying a current of 10 amps toward the top of a page, and is affected by a uniform magnetic field. The force acting on the wire is 0.6 newtons, directed to the right of the page. What is the magnetic field strength? So let's identify some of the things that we are given here. Starting with, it's talking about a wire that is 1.5 meters long. So this is telling me the length of that wire, which is symbolized with a capital L. Okay, it also tells me that it is carrying current of 10 amps. So, telling me current, and we know that current is I. It's directed to the top of the page in a uniform magnetic field. The force acting on the wire is 0.6 newtons. So that is telling me the force. And then it's ultimately asking me, what is the magnetic field strength? So, in other words, I need to find the magnetic field, which is B. Okay, so now I'm solving for B, and I've got F, I, and L. The only equation that has I and L in it is my second equation up above, and it's F equals B times I times L, F bill. Okay, so let's plug in what we know. We know force is 0.6 newtons. B is unknown. Current is 10 amps. And the length of the wire is 1.50 meters. Now, remember that length, just like distance or displacement, is always measured in meters. So, do not forget that if you are presented with something in centimeters, it needs to be converted. So just a helpful hint, there are 100 centimeters in 1 meter. So if I'm given an answer in centimeters and I want to convert it to meters, I take whatever is given to me in centimeters, divide it by 100, and that gives me my answer in meters. Okay, so use that moving forward. You might have a situation on pages 7 or 8 where you're given the length of wire in centimeters. Make sure you convert that to meters before anything else. Okay, so back to the problem. I'm solving for B, and I've got 10 being multiplied by 1.5. these are all multiplied by each other, so I need to move them to the other side by dividing them by themselves. So what I end up with is 0.6 divided by 10.0 times 1.50 equals B. So when I do the math, plug it into my calculator, I get 0.4 Tesla, my unit for magnetic field, equals B. All right, and let's look at our last. If I look at the right side here, here's our other equation, and here's an example of a transformer. Okay, so a transformer can either increase voltage or decrease voltage depending on the amount of turns on a certain side of the coil. Okay, so if we're reading this from left to right, I've got the left side, which is known as my primary coil. I've got the right side, which is known as my secondary coil. So you'll notice that on the left side, I've got 1, 2, 3, 4, 5 coils on the left, and on the right, I've got 1, 2, 3, 4, 5 also. So the amount of coils on the left are equal to the amount of coils on the right in this case. So my equation says primary voltage divided by secondary voltage equals primary coils divided by secondary coils. So we're counting the number of coils, the number of loops that are on my primary side compared to the secondary side and the number of coils on that side. So the abbreviated version of that equation is Vp divided by Vs equals Np divided by Ns, where V represents voltage, N represents the coils, and P and S in this case stand for primary and secondary. So we'll look at one of those examples here in a minute. Example here, and again it's related to a transformer. Here's my problem, my equation up here at the top, and the situation is telling me says a power line carries 50,000 volts before it's stepped down to 110 volts as it enters a house. If the house's secondary coil has 100 turns, how many turns does the power company's primary side of the transformer have? So this word right here, stepped down. Stepped down means to decrease. Okay, so anytime you have something stepped down, that means the voltage is decreasing. Anytime that you have a situation where it says it's being stepped up, that means it's an increase in voltage. Okay, so the power line carries 50,000 volts before it's stepped down to 110. So it starts off at 50,000 and ends at 110. So the primary side, the initial side of my transformer, has a primary voltage of 50,000 volts. So Vp equals 50,000 volts. And it's stepped down, it's decreased to 110. So that means my secondary voltage has only 110 volts. It says the house's secondary coil. So it's telling you that this is on the secondary side. It has 100 turns. So remember, turns is expressed with an N. So let's go ahead and list Np and Ns. The secondary turns is 100. And I want to know how many turns is the power company's primary side. So that's Np, primary coils. So I'm going to set up my equation. Vp over Vs. So primary voltage divided by secondary voltage equals primary turns divided by secondary turns. So now when I start to plug in what I know, my primary voltage is 50,000. My secondary voltage is reduced down to 110. Equals my primary coil, my primary turns is unknown, so I'm going to write it as Np. And my secondary coils, I do know it's 100. So now I've plugged in everything I know in my equation. Now, since I've got two fractions, all I have to do is cross multiply. So I'm going to cross multiply these two and then cross multiply these two. So 50,000 times 100 gives me 5 million. And 110 times NP, primary turns, is 110 NP. So if I want to get NP by itself, and it's being multiplied by 110, the opposite is to divide by 110. So I get 5 million divided by 110 equals primary coils. So 5 million divided by 110 gives me 45,454.55 turns, or coils. So that's how many coils are on the primary side that are receiving the 50,000 volts of electricity. So far we've done one example with each equation. We've completed the data table. Use those three examples and the data table to complete the answers on pages 7 and 8. Remember, these will be clicked in Tuesday when I return.